Let's start with the joint cumulative distribution function of two random variables x and y. It's defined as the probability that the random variable x takes on values little x or less, and the random variable y takes on values little y or less. It's a monotonically increasing function between 0 and 1 with values at the boundaries, as we know very well. At negative infinity for x, the distribution function is 0, whatever the value of y may be. Likewise, fxy at x comma minus infinity is also 0. The function reaches 1 at the limits infinity for both of them, and when you set one of the variables at infinity, what you get back, which we will see in the next slide, is the marginal distribution function for the other. So fxy evaluated at x comma infinity is nothing but fx at little x. Similarly for fy at little y. Also for any b greater than a, the joint distribution function, keeping the y fixed, would be greater for b comma y than a comma y. And likewise for x comma b and x comma a, as long as b is greater than or equal to a. The interpretation could also be given in terms of the probability masses or densities. So if we want to evaluate the distribution function at fixed values of x and y, little x and little y, we would add all the probability masses, the joint probability masses for x's and y up to the respective values. And if the random variables are continuous, then we would integrate the density function up to the limits little x and little y. This also tells us that we could invert the relationship and show the density function as the differentiation of the distribution function. And likewise, we could get a similar expression for the mass function in terms of the distribution function. We now move on to the mass function and density function in a little more detail. So the mass function is the joint probability that the random variables take on the particular values. So p of x comma y is the probability of intersection that x is equal to xi and y is equal to yj, and that would be the interpretation of the joint probability mass function. Likewise, the density function would be approximated as an elemental probability if I take a little area around that, delta x and delta y, and multiplying the density function with that elemental area would give me the probability of finding x around that point and y around that point, whose size is respectively delta x and delta y. If I now expand this idea over a region, so if I want to find x and y within a region defined by capital A, then I could sum them in the discrete case for all those values of x and y that belong to the region A, or I could integrate the density function in the continuous case for all those values that belong to the region A, where the indicator function I conveniently takes on the value 1 if the point is within the desired region A, otherwise 0. This discussion we cast in the format of a pair of random variables x and y, but we could generalize this to n dimensions. So we could define the joint distribution function for n random variables x1 up to xn in terms of the joint probability, the probability of the intersecting events, that capital Xi is less than or equal to little xi for all the i's. And likewise, we could define the joint probability mass function and the joint probability density function for the group of n random variables. The marginal and the conditional probabilities are defined similarly as we did in the case of the univariate random variables. So the marginal CDF, as I said, is simply when you put the argument of the other one at infinity. The marginal PMF is obtained by integrating out by summing out the other variable. The marginal PDF is obtained by integrating out the other variable. So these are the equations that you see on the screen. We could define the conditional mass function similarly, just as we define probability of A given B. So here it's the same approach. P of x given y has taken a particular value little y would be the conditional PMF of x given y, and that would be the ratio of the joint mass function divided by the marginal mass function. We could, just as we did in the case of P of A intersection B, we could describe the joint mass function as the product of the marginal and one of the conditionals. So P of x comma y would be P of x given y times P of y at the appropriate arguments. We could do something similar for the density function. The density function of x given y at a particular value would be the ratio of the joint density function and the marginal density function. And like we did in the discrete case, the joint density function is the product of the conditional density function times the marginal of the other. So f of x comma y is f of x given y times f of y, or equivalently f of y given x times f of x. We have to be a little careful when we come to the joint CDF or we come to the conditional CDF. So if we want to fix the value of y and then find the probability of x would be less than or equal to little x. So that is the definition of my conditional CDF. Now we can expand it just by using the definition, but we have to be careful that we cannot write the joint distribution function as the product of the conditional and the marginal. You have to be a little careful for that, and why it should be clear from the above two equations. We could continue in this line and describe the cumulative distribution function of x given a particular value of y, so that conditional CDF of x we could, in the discrete case, define as the ratio as you see on the screen, and for the continuous case define as the ratio as you see on the screen. In the first case the numerator is a sum, and in the second case the numerator is an integration.